I will quickly show a bit like how we do the data processing and how we calculate maps with extrapolate. I thought, 15 minutes, I can show plenty of things. So I tried something last week, took 4 hours, so I kind of shortened it down. And so I decided to show a bit of data processing with crystallography. And I thought it might be most useful if we just basically use the same data that is used in the crystallography tutorial, so that if you're interested to do it yourself, that you can find more or less the same data, and that you might get some connections to what I say right now. So you just Google crystallography tutorial and you land on this. So this will be with crystallography 0.11.1. I heard that version 0.12 will be coming out soon, so there might be new features in there. So in this tutorial, they use data from an experiment that was carried out at the Swiss file, and the data can be found over here. Let me just start my, no. So the data is stored in the CXI DB. Yeah, people can deposit their raw data there as well. And so this was done also for this experiment. And you can find everything you need to reprocess the data over there. Now, quite some, so this is from data from this publication. So that's Carol Nas who did the data processing and submitted the data. And it will be on this, oh, sorry, wrong table. It will be on this protein, so this A2A. And they collected something like 2 million images. So if you're going to download that all to your computer, I mean, you will need quite some memory. So what we do is we just do the data processing with a subset of the images, and it will be like 1,382 images. And so I downloaded one of the data files. Is this visible? Yeah. So this is one of the data files, and it's an H5 format. So it means it's a single file which contains multiple images. So it's a kind of like containerized format. So we're going to use that. And then in addition, we need to have the geometry description. And also that in the crystallography tutorial, they tell you where you can find it. So the geometry description looks a bit like this. So you have first some general information about like how to read out the data, the resolution, so that's depending on the pixel size. Then you have this CLN, that's the camera length, so that's the distance between the crystal and the detector, which is something that we very often need to optimize during an experiment, and also afterwards if we do the offline data processing afterwards. And so we basically do that with changing this value and then reprocess the data until we find the best value. So what do we call the best value? Well, that's when we have the most, when we can index most of the images, and also when the spread on the unit cell is the smallest. Then we have another value, which is the photon energy, which is a single value here, even though at XFELS there is some spectral variation possible. Then we have some information about the mask file. So if you want to mask out specific pixels, you have to send it out here, how to read it. And then we basically have different descriptors of each of the panels. So basically, where is each panel located? Where does it start? Where does it end? And if there is a specific offset to it. So we're going to start crystallography. Already tried it before. Yep, so here is the window opening. And so we can load the data. So press load data. There's different ways to load your data. You can have an input file you can have a file list which contains like all the locations of your input files. But since we're just going to look at one input file with multiple images, we can select an individual input file. So that's this one. And indeed, it asks also for a geometry file, so we can find it over here. We press import, and so now it imports all the images. So we can see over here, I hope my mouse is clear, yeah, that there's like 1,382 images, and we can use these buttons here on the left to jump from one image to another. So you can see, let's make this a bit smaller, different images. Some have very nice and a lot of spots. Others have a bit less spots. And you can see on certain of these images we have these yellow squares around the spots. And these are the predicted or like the peaks that are detected. Now you can see that definitely not all of our spots are detected. So these default values are definitely not okay for what we're going to do. So we're going to find a nice image. I think this looks okay. And we press peak detection, where we can find different parameters to change and to play with to find the best peaks. The aim is indeed to select most of the peaks, but what's more important is that you don't select any noise. So you try to play a bit with the parameters so that you find most of the peaks, but if you're going to select noise as peaks, then this will probably mess up with your indexing and it will decrease your success rate. So the most popular algorithm for peak detection is Peak Finder 8, and so it will change to specific values. By the way, if you're like, we're now using the graphical user interface, but if you want to use the command line later on, what is very nice is that when you hover over specific parameters, you can find the command line parameter. And if you would then go later into the CRIS file manual, for example, index imagic is a main parameter, you can find those specific more information about all these parameters that you want to alter. So it has a value for the threshold, so it means like, okay, what's the minimum value that we need to have a peak? And another parameter to play also with is the signal to noise ratio. So to find the threshold, what we're going to do is we're going to zoom in quite a lot until we see the values. And I'm not zooming in on a peak here, I'm zooming in on the background, because I actually want to know what the background value is so that I can just take a value which is a bit higher and I know that that will be a peak. So we can see here that the background here, at least in this middle center, goes to like 60, 70, and so on. But here in the middle we have a lot of a very high background because of probably the medium that was used for the crystals in. So if we zoom in over here, we will find much lower values. So basically we want to select a value where these peaks, which are like in a lower regime, are selected, but also the peaks over here are selected. So we know over here it's about 60 or something like that. So the value of 800 is definitely not good. So we can try something like 60, and if we do that, we can see if peaks are selected. So indeed, our peaks here are selected. Why are we not like selecting a lot of peaks over here, which might have a value of at least 60? That's because we also have this signal to noise ratio. So if I would now decrease the signal to noise to a very low value, like 2, you get this. So this is definitely something that will not get you anywhere. So you most of the time, a value of signal to noise between 4 and 5 might be okay. But it's like, that's the reason why even if you're like a very much familiar with CRISFEL and you like to do everything command line, it's very good to open your images and see actually what you're doing. So we can go back to maybe a value of 5 to have something much nicer. And this seems to be fine for this image. Sorry, I forgot to say in the beginning that in this geometry file we also had a mask file. And for example, this panel here was not working. So it's very important that this is masked out. because if anything is weird happening on this panel, we don't want to take that into account, and we definitely don't want to integrate Bragg reflections, which can be predicted to be over here. So this seems to be not too bad, even though here there are some peaks which are not selected. So maybe we can decrease the threshold still a bit lower. Then you have other parameters, such as the minimum amount of pixels that you want to have in your peak. So this is again helping you to prevent that you're going to select a lot of noise. So if we zoom in on a peak, we can clearly see that most of the peaks have more than 2 pixels, right? There's a maximum number of pixels, 200. I don't think we will have a peak of more than 200 pixels. So as I said, it's not that dramatical to not have selected this peak, for example. The most thing is that everything that we select is a peak. So this seems to be fine for this image, but of course we don't know how it goes with other images, so we can go to another one. So overall, these parameters seems to be fine. So, but to really know if these parameters are okay, we can try just to index a single frame. So we index just a single frame, not everything at once. And we see if this works. So this opens up another window. Maybe I should close this first. Where it's going to ask us for the parameters for indexing. So indexing is really now finding the Bragg reflections on our image, given the positions of our peaks. Just to index a single image, we're going to not give it any more information about the unit cell, but later on we will give some information also as well. So Crystal has different indexing algorithms, and by default it will select all of them. And that means that it will first take this one, Diracs, and if it cannot index an image, it will go to the next one, which is Mosfoam. If that doesn't work, XDS and XGandalf and so on, until it can finally, or give up or found an indexing solution. Now we're not going to do that. We're just going to select a single one. If you don't have any unit cell information, then Mosfoam is probably the best one, but the most popular one is XGandalf. For that we need to actually give it a unit cell information, I think. So let's do Mosfoam then. There's some additional parameters, like it might be that we have hit multiple crystals at once. There's another option to find multiple crystals within a single diffraction image. Also like to try more, if it doesn't find an indexing solution, it can delete the most weak spots and try again. These are all these options here. We're just going to leave it as such for now. If you want to know more about all of these parameters, you will have to read the manual. So we just press run. And what we see now is that here at the bottom, it says that it found a crystal, and it gives you the unit cell parameters. And we also have other things on our image here, which are these circles, and these are the positions of the reflections. Now, so based on the few spots that we have, we can index, so try to get the unit cell parameters, and we basically know where we expect reflections to happen, to be located. So these are all these positions. So even if we zoom in here, for example, it might be that it's not so obvious that there would be a reflection here. So here, honestly, I'm not too sure if the indexing solution is that great. Even though wherever we had a peak, it is nicely predicted. We can also do that on another image to see maybe something with some more peaks like this, where we have these very nice separated lines. Try this again. We index this frame. So that works as well, but in this case it looks like a bit chaotic because it found 2 crystals. So sometimes it can be a bit difficult to from these kind of things to see like, okay, is this a proper indexing solution or not? And actually, it's very difficult if we have multiple crystals. But overall, the locations that we have selected, they fall between the predicted positions. And for example, here we can see that also certain positions which might be other spots are also predicted, so that's good. Actually, this is not too bad. So we can see that this was one of those peaks that we selected. This one we did not select, but it's also predicted. So that's actually a good sign. Now we can go to another image. I'll zoom out a bit. Do this again for every image, but if you have millions of images, you basically don't want to do that for every image manually. Just to say that playing with these parameters, like for peak finding and then the parameters for indexing, is something that takes quite some time. But it's only just a very quick introduction of what we do here. So I know that these parameters should be more or less fine for this case. So we can index all frames. And now we have to give it a name for an output directory. So I call it run1. And we're going to give it cell information. I opened it. So we're going to give it unit cell information. So that's this crystal unit cell file. We're going to give it the lattice type, which is orthorhombic, the centering type, and then the axis of the unit cell. So that's the A, B, C, and then the angles. Since this is an orthorhombic cell, the angles are 90 degrees. So this is also the information that we're going to give. So we're not really giving the space group. We're giving the lattice type, the unit cell, and the centering type. I put the cell in here. Now, instead of MOSFEL, we're going to use Xgandalf, which is the most popular one. And so we can tell it that it can use prior unit cell and lattice information or not. Then we gave it information about the unit cell, but we can also give it some tolerance, like the angles should be within 5% of the values that we give, and the angles should be within 1.5 degrees of the input angles that we give. So we are allowing a bit of variation on the unit cell that we give it. For integration, we're going to also keep everything default. There are like advanced indexing options, but basically it tells you like if you want to do advanced indexing options, you're going to use command line. Then if you are running crystval on a cluster, like we saw before for the European XFAL, you connect there and then you can basically run on a cluster, let's just say Slurm, and then you get some parameters here. But in this case, we're just going to run this locally on my computer, and we're going to try to speed up with giving a bit of computational power. So I'm going to use 12 threads in total. I'm going to press run, and in the meantime, I can give some other information. So now it's going to try to index those 1,382 images, and we have this progression bar over here. That should take a few minutes. So if you look like what's happening right now, so this is my output folder. It generated an additional folder which is called Index Magic, which is the major program for indexing in crystval. That now has 12 workers running for me since I asked for 12 threads. And we have an output folder which is called run1 cell. That is the file that I gave. This contains some information, so just a copy of the geometry, a file list, so with the input file. Then this Miller data is something that's written out to optimize your detector geometry afterwards if you want. Then there's like, a file with all the parameters. Then there is a file that contains all the parameters that you used to run it in as a command line. So if we open that, I'm just going to open that in a terminal. We call it run1, like this. So this is basically going to give like all the parameters. So again, if you want to just use the GUI to like find good parameters and then use command line to further process your data, you know basically exactly what you need to give it from parameters. So for example, we used a threshold of 55, the minimal signal noise of 5. We used Xgandalf for indexing. These is this tolerance values. Yeah, and as I said, like we're not going into all of the details of the parameters here, but there's like quite some parameters to play with. Yep. And then we have some log files. But then the first file that we had here is the crystfile.stream. So that's the main output file of crystfile. So that's interesting also to look at. So while this is running, we can have a look like what is in this cell. So again, we look at what's in this file. So this is actually a very long file. It's just plain text. So the crystfile header contains, again, all the parameters that we use to run it. So again, if you want to afterwards run the command line, it's very easy from here to take the arguments and run in this way. Additionally, it's also very good logging because 3 years later, if you did not write down somewhere like which were the parameters that I used, it's written in this file. Then it will copy your geometry file. So again, this is very important information since we might change this geometry file once in a while to optimize these distances, to optimize the position of the detector panels. It might be useful to remember indeed which file was used and what were the parameters. So yeah, again, we have this, like for example, this camera length. We have the position of the panels and so on and so on. So we go a bit down. This is a huge file. Good. Then if we gave crystfile unit cell information, that will be repeated over here. So again, we have exactly the same information like the lattice type, the centering, and the angles. Then it will again say which indexing methods we used. And then there will be repetition of blocks. And per image, it will like, an image is called a chunk. So it will start a chunk. It's this image. I mean, it's always the same image. And within this file, it's image number 8. If it could be indexed, it will tell you indexed by, and then in this case, Xgandalf, because this was the only indexer that we used. If it cannot be indexed, it will just say indexed by none, so it could not be indexed. Then we have information about the peaks that we found, so with the parameters that we set, so peak finder 8, a threshold of 55, and a signal to noise of 5. We found 19 peaks, and these are their locations. So after the peaks list, we have another begin something, which in this case is begin crystal. So we could find a crystal. So it means that if we could index an image, we found a crystal. So these are the cell parameters of that crystal. Take care, we like to think crystallographers like things overall in angstroms, but take care, sometimes it might be reported in nanometers. So this is the cell parameters in nanometer. Also, we have them in reciprocal space. There's some other information, which is not the most important one. And then we have this information about the reflections. So for each reflection, we have their index, HKL. We have the intensity, we have the sigma, and then we have more information on the peak, the background, and where they could be found on the image. So we basically have a whole list of peaks, right? Remember, for this one, we only had 19 peaks, and still we found a lot of reflections. So crystfile will, as I said before, once we can index an image, it means that we basically know where to expect a reflection, and it will give the positions of all these reflections and also integrate these. So it means that even if there's no signal at all, it will be integrated at that specific location. So that's why we have a huge list. So it basically goes to the borders of my image. Oh, this is huge, yeah. Until we get to the end of this crystal. If another crystal was found on the same image, so if two crystals could be indexed, we again have begin crystal, the list of reflections, and end crystal, until we have here finally end chunk. So this was the indexing or the processing of that image, and then we can go to another image, which is image number 10. So basically this file is always a repetition of those kind of things. Good. In the meantime, my indexing here is finished because the here was cancelled before and now it's across, so I can close it. And here we're going to show the results from our run that we did before, so run 1 cell. So that means that now for every image, I can look at the indexing results. In this case, we have basically indexed everything, and that is because the authors did not deposit all the 2 million images, but only the images that could be indexed. So in this case, we actually found a very, like, if we click on next image, we will always find indexed images. So if you have a very low indexing rate, it might be that you have to click on quite some time until you find an image that actually contains the fraction plots and is nice. Good. So now that we've done that, we can go to the next step. So we're going to determine the unit cell. Even though we knew the unit cell before, it's always a good idea to look at this. Did it open? It did open it back. So here are the distributions of the unit cell. So we can zoom it a bit. So what we can see is that we have a very sharp peak for every of these unit cell parameters, and that is a symmetrical peak. If that peak would be skewed or so, then it's mostly a sign of that you have that your geometry actually has a problem. Now, what we're going to do is we can select these peaks. Fit the unit cell parameters to it. So these are actually very close to the unit cell parameters that we gave it as the input, but it's good to redo this and have the exact unit cell parameters, or the best unit cell parameters for this specific data set. And we can save this unit cell, so we're going to do it run 1. So we're going to say that this is the cell file of this specific run. And again, we're going to enforce the fact that this lattice should be orthorhombic, so the angle should be 90 degrees. So we can save it and close this one. Now then there's a lot of other steps which will take quite some time, so I will skip them, but it's about refining the detector geometry, so really the placement of the different panels. So for the distance between the crystal and the detector, we change the geometry file and we just rerun the program again and again until we find the unit cell parameters that gives us the most indexed images and the lowest spread on unit cell dimensions. Then if you had this indexing ambiguity, remember Mr. Bean, we can try to solve it with the tool over here, but we go directly to merging of the reflections. So we have different models to merge, to scale and merge reflections. So the simplest one are this process HKL, where we just average over everything. And then we have this X-sphere, which is the full post-refinement. And then we have kind of something in between, which is the Unity model, in which we will not try to assign partialities, but still we can do some more scaling. So I'll just take the simple merging because that will be the fastest one. So I do merge, and this is going to be the Monte Carlo method. We have to select our symmetry. So this is, again, the orthorhombic symmetry. In the specific case, we're going to merge the Friedel pairs. yeah, basically it means that the reflection HKL is supposed to have the same intensity as a reflection minus H minus K minus L, so basically the symmetry, unless you have some anomalous diffraction or dispersion in which the part of the X-rays will be absorbed and re-emitted and their intensity will not be the same. But in most of the cases, these intensities will be the same. And then it means that we can average more reflections, and so we'll have a stronger data set. We're going to keep, again, the default parameters, but we're going to, again, give it 12 threads to hopefully have it very instantly. So we run it. And it's on. So if we look again in our output folder, we have an additional folder, which is this one. It again has a run merge, so that if you want to do this in command line, it's very easy where to find the parameters. And now we have this HKL file. So let's just open that. So this is the file that we basically want. So we have each reflection HKL. We have the intensity. We have no phase information. We don't remember phase information is not measured during an experiment. And then we have their error values, so the sigma. And then here we can see the amount of times this reflection was measured. So in this case, it's like, yeah, reflections are measured basically only a few times. So what we did here with only 1,300 images is not at all that great. If you go back to the publication that came with this, it's like they processed 2 million images, and they had 200,000 index images. We're only working here with 1,300 to get something. So yeah, we don't have such a great coverage of the data. Here they report the average redundancy. So the redundancy is the amount of times we measured that reflection, or we measured part of the reflection. So that's like 800. So yeah, the values that we have here are definitely not good enough. However, we get our list with intensities and standard errors, so we can do something with it. The next step would be to calculate your figure of merit, so your statistics, like is the data set good or not. Explaining all these parameters will also take quite some time, so we'll not do that, but we're just going to export the data into something that we can use. So this is data from Crystfile. We want our merge data from merge Monte Carlo. And you want mostly to have that in a format which is called MTZ, which is the format that can be used by other programs later on. We're going to give it the unit cell information, the one from our run. And then we're going to save that file. Here, Crystfile is telling us that it does not know the space group, so it only uses the point group. And indeed, if you're going to look into our file over here, it's going to assume the point group C222, which is basically the lowest space group that you can have with an orthorhombic centered cell with the symmetry, these 3 symmetry elements, so the rotational axis that we gave it. However, if you look into the publication, the real unit cell is C2221, so this is the rotation axis. So it means that with this data, we still have to find out if we, like, what the real space group is. So this is very important also to run a program like a pointless, aimless, or something like that, to get the real space group and yeah, just to work with the real space group, which will otherwise give you problems. So that was very quickly on how to use Crystfile. So again, if you're interested, you can go through the full tutorial, which is over here. By the way, that data file that I downloaded, so that's a single file. Nevertheless, it's almost 100 gigabytes, so still you need a bit of space on your computer to download that. so yeah, it will basically go over the same things. We directly process the data using the unit cell information. The tutorial will also explain you what to do if you don't have that information. So if you can have that information from a standard crystallography experiment, but if that could be performed at cryotemperature, and at room temperature it might be that your unit cell changes a bit, and so you might need to take this into account and maybe process first your data without a unit cell. And for that then I would recommend using MOS film instead of X-Gandalf. It will give you much more details, but it will take you a few hours to go through it completely, but it will give you a very good overview. Good. With that, we're going to close the Gristfeld part. No, we don't want to save the session. So if you did the data processing for both your dark state and your light state, we can calculate Fourier difference map and extrapolated structure factor amplitudes with extrapolate. So that's what we're going to do right now. So I don't have that much time left, but I'm going to go very quickly. So extrapolate can be just found on GitHub. So you just do GitHub extrapolate. You come to this page, which explains you also how to install it and how to launch it. So we're going to use the data that was also used this morning in my presentation. So that's fluorescent protein, which has a chromophore in its center that undergoes a large isomerization. In the publication of extrapolate, we explain that extrapolate comes with some different modes. So we have FO only, fast and furious, and calm and curious. So the main steps in extrapolate, the first step is importing the data. It's a bit boring, but essential. Then we calculate the Fourier difference map, and we use a tool which we call Map Explorer to analyze the difference maps. Then we can calculate the extrapolate structure factor amplitudes. Again, use that tool Map Explorer, and then by comparing the output of the analysis of the difference map, we can estimate your occupancy. Now you can see these extrapolated structure factor amplitudes. You have multiple errors here. That's because we're going to calculate them with different values of alpha, so that different occupancy-related values. In the FO only mode, we will just do step 1 and 2. In the fast and furious mode, we do all the blue steps, and with the most optimal occupancy, we will do some automatic refinement. In the calm and curious mode, we actually gonna do refinement with all the different extrapolated structure factor amplitudes that were calculated with these different alpha values, from which we can then also have another method to estimate the occupancy. A bit lower in the publication, you can find some kind of like flowchart that we suggest to use. So you first run extrapolate in FO mode. You try to see if things are fine. If that's fine, you can use it, run extrapolate in fast and furious mode. And if that's fine, you can go to the calm and curious mode. So we have 10 minutes, so definitely no time to do that. So we'll just do a very, very quick demonstration. So we're going to use the data from MEOS4B, so that fluorescent protein. There is not yet a tutorial of extrapolate online. I basically have one. I just have to put it online, but there were a few technical things, so that's why it's not yet there. But I promise it's coming. So I could just download the data from the protein data bank. So what we have here is everything is in CIF, which is crystallographic information file. It's the more recent file type, which will replace the standard PDB file, but also these structure factors can also be provided as CIF. So just from the protein data bank, I downloaded the reference model. I downloaded the structure factors of the reference state, the structure factor amplitudes of the triggered state, and then I have some other files which contain restraints for ligands. So most programs understand, like, okay, a standard amino acid should have this ideal bond length, these angles, and so on. But for example, my chromophore, I have to give this information myself. Good. So that's all the input that we're going to use. Seems a lot, but normally it's pretty fine. So we launch Extrapolate using the Python that comes with Phoenix to have access to the CCTPX. Good. So in the first step, we have input-output, so we can add the files. So I'm going to add.
Can you show again what command did you wrote in the command line?
Yes. So the command is Phoenix Python. So you should have installed Phoenix. And then if you, actually the installation of Extrapolate is just downloading everything. And then there is a specific Python script to launch it. So it's not that standard, but should be easy. It's also on the GitHub webpage. I'll tell you, like, okay, what you need, and then how to launch it. So you use Phoenix Python, and then this script if you want to run the command line, or it has been a while since I looked at this. Oh, or x8_GUI to launch the graphical user interface. We can look at it together later if you want to find it. So we'll add the data files. And so, yeah, okay, it's readable. Extrapolate will try to estimate what data type it is, but nevertheless we have to check it. So this one is indeed one of those restraints files. This one is my input model. This is again restraints. This is my reference data. This is my triggered data. So yeah, normally you know which files you're working with, right? So now you have to assume that these are the files, the correct files. We can give it output directory, so we can say run 1. We can change the resolution, we can change output prefix, but again, we're going to keep things default to keep it simple. So the next tab, which tab contains FOFO extrapolation, where you can find the different parameters for your Fourier difference map and your extrapolated structure factor amplitudes. So by default, it will run in the calm and curious mode, but as I said, you have to be calm but curious. But you need to have some time. So we definitely don't have time, so we're not going to do that. We can run it in the fast and furious mode, and in this way, specific parameters are basically disabled, so we will use default values for quite some things. And if you just want to calculate a Fourier difference map, you can just run it in FOFO only mode like this. And it basically will be finished in a minute or so. So what we're going to do right now is let's just run it in the fast and furious mode. So there will be certain things which have the default values, such as this Bayesian weighting schemes. We can select the lowest occupancy that we're going to look at. So let's say that we want to go from an occupancy of 0.1 to 0.5, and we want to test 10 different occupancies in between that. The values here, this is like to how to integrate our difference maps. We're just going to keep that default as well. Then we have another tab which is concerning refinement. So it will do some automatic refinement. You can choose a program here. So you can do real space refinement in Phoenix real space refine or in Qt. Let's keep Phoenix real space refine, and we'll just do a single cycle for the sake of time. And reciprocal space refinement can be in RefMac or in Phoenix Refine. And in each of the case, we have selected some parameters to change. So again, we could just do one cycle just for speed, and then we press this little running guy, and then it's running. With that, another tab will be opening. So the first one will be the log file, so where you can keep track of what's happening. There will be a main tab, which will depict figures. Now, since these will be updated during the run, they kind of disappear, so I hope that doesn't happen too much. There are several figures. I will just pick out a few which are important, and the first one is this one. This contains information of your R ISO value and CC ISO value. So R is a residual factor, and CC is a correlation. So residual factor, you basically want to have that as low as possible. A correlation coefficient, you want to have that as high as possible. Now, what is this showing us? It's the isomorphism between the two data. So as I also said already this morning, we basically want to have these two data sets as similar as possible. There's only a few atoms that are moving. The global structure of our protein remains the same. Even if you have a full helix that's moved, the global structure of a protein remains the same. That means also atoms are not moving in and out. So it means that the structure factor amplitudes should basically be the same between the two states. We expect only very small differences. And so that's what is measured with this isomorphism. So if the structure factors are very much the same, we have high isomorphism, and so then this R value should be low. So especially at low resolution, which we can find over here, we want this value to be low, right? The global structure of my protein remains the same. At higher resolution, there will also be some more noise, and this will rise. Now, if this really goes asymptotic, or it really becomes like a curve that goes up and down, it means that from there on the data is not really trustworthy anymore, so it might be better to cut the data. Now, in this case, we have an overall isomorphism of 10%, which is generally seen as good. And at high resolution, we go to 25%. You could tolerate like up to like 30, 40, maybe 50, but then we already have like very high residual factors. Then we have some other plots. We're not going into detail a lot. What we see here is a one-dimensional plot of your structure. So here we have just the amino acid chain, and then in blue and pink we have the secondary structures. And on top of that we have the integrated peaks that we could find in our Fourier difference map. And so without looking into Qt or any other program to visualize the map, I can already see that I have specific peaks, that have peaks on specific locations. For example, here, in the ligand step here, I can find waters, but also this is the code of my chromophore, so I can find a very large peak on that chromophore. And this gives me an overview that I have peaks on specific locations, which is basically what I want. I don't want to have peaks all over the unit cell, because that would just mean noise. So when I see this, I'm already like getting excited that I have good maps. Then let's see if we need to update this. Then here we have the results of the alpha or occupancy determination. So again, we use alpha equals 1 over occupancy. If you use another relation between this extrapolation factor and the occupancy, just don't look at the right part, just look at the left part and do your calculation yourself. So there's different methods. Here we have methods that basically compare the difference map. So we have our Fourier difference map, which is what we call like the real truth. It really shows the difference between the two states. And then we have all these extrapolated difference maps calculated with a different occupancy. And we assume here that the difference map, which resembles that Fourier difference map the most, will be the best alpha value. So will be calculated with the best occupancy. So this is shown here, and there's two methods. One is called the maximization, and the other the Pearson correlation method. Again, I'll have to, please read the documentation or reach out to me later. Then we have a tab for occupancies, where we have something about negatives, completeness, signal to noise. Let's see if we update this. This is still running. Okay, since this is still running, I'm going to load results so that we just couldn't go back. So I have a backup run, which will be opened as run 2. So here we can find that it found a best occupancy at 22%. So if we go to 22%, we can find a button to open the results in Qt. So that's the visualization window. Right now it's still Qt 0.9. I will have to update the scripts to the newest Qt version. So we have quite some things here. let's not go over everything. So we have a lot of maps, a lot of models. But basically, we have our input model over here. And this is the Fourier difference map. So if we zoom in, we can basically see that we have the peaks indeed of these locations. Now, this is something, what I typically like to do is I like to disable my model and zoom a bit out. And now I just start walking through the unit cell. And if I change a bit the contour level like this, what is clear now is that I have peaks on specific locations. So again, this is a confirmation that I have peaks here and not there. So with doing this, so if I, for example, scroll here so that I have quite some variation in my map, I can basically see no, now I'm looking at noise because I basically have peaks everywhere over my model. So if I change my contour level so that I have only the most strong peaks, I know these are clearly above the noise. So even if the standard is to show a difference map at 3 RMSD, in this way I'm sure that whatever I'm looking at is the noise level. And then I can zoom in again and maybe can change again the contour level a bit. So what we can see here, this is being removed in my triggered state. This arginine is moving over there, and this histidine is also moving over here. Then we have all the results of refinement, the other models, so we keep just the input model. And then the other maps here, these are my initial extrapolated maps. So let's just quickly change that color to blue, which is what most crystallographers like. So here now we have the extrapolated map, so this is still unrefined, where we have this difference map. So the difference map, so in green and red, resembles that Fourier difference map a lot. And then we also have, or let's say equivalent of the standard 2F4FC map in which we can model things. And then we have another map from refinement and other models from refinement. Now, in this particular case, the conformational switch is that large that the automatic programs did not handle it properly. So I will have to intervene manually. Anyway, at this point is where the program stops and where you have to refine your structure yourself to get to that final, to your final structure. So 50 minutes are over, so I'm gonna shut up. And so if you have more questions, feel free to ask me. I know this was very quick. So basically, we don't do data processing and map calculation in 50 minutes. That's clear.